Hello there, young students of chemistry. This is a quick recording regarding um, how we find out what the formula for a compound is. Long before we had rules of nomenclature from the IUPAC, which is the International Union for Pure and Applied Chemistry, the way we determined what was in a compound was we tested it. And testing it in a laboratory and determining composition, and then calculating what we have here today, the empirical and the molecular formula for the compound. And as you see, the definition of empirical formula is the smallest whole number ratio of elements in a compound. And in your lab tomorrow, you will find that for yourself, that this is something that is not terribly difficult to come across, the empirical formula for a compound. And for all ionic compounds, what we would have written using our rules for the formula unit is the empirical formula for the compound. Now, covalently bonded compounds are a little bit different because we're not talking about just a ratio of ions that are attracted to each other, but an actual bonded molecule. The molecular formula is sometimes not the smallest whole number ratio of the atoms in the compound. So the molecular formula is how the molecule really is. You know, we know that hydrogen peroxide, H2O2, is really bonded with two oxygens bonded to each other, and each of those oxygens having a ligand of hydrogen. And it is a whole number multiple of whatever the empirical formula is calculated to be. So we can see here that there is the formula for hydrogen peroxide. That is a molecular formula because the subscripts that are in that compound can be reduced. 2 and 2 reduces to 1 and 1. So the empirical formula for hydrogen peroxide is HO. The empirical formula for a sugar, we can see here that this is a molecular formula, C6H12O6. That can be reduced. If we divide all of our subscripts by 6, that ends up with C1H2O. So that is the formula for a sugar, and a sugar is a carbohydrate. You've probably heard of carbs. Carbs are compounds that all have the same empirical formula, CH2O. So just to be able to recognize an empirical formula or a molecular formula is something I expect you to do. If the formula is molecular, I would expect you also to be able to look at that molecular formula and reduce it down to its empirical formula. Beyond that, I would expect you to calculate empirical and molecular formulas. Oh, I'm sorry, I didn't realize there was some practice on this. So we can see here that this C4HO2 is an empirical formula. Because we have this subscript of 1 on the hydrogen, this cannot be reduced any further. So this is an empirical formula. C22H44O11, those subscripts can be reduced if we divide them all by 11. So this is a molecular formula. And if we wanted to write the empirical formula, we would just divide those subscripts by 11. So that's going to be C2H4O. CH4 is the formula for methane. We have a subscript of 1, so that cannot be reduced any further. This is an empirical formula. Calcium sulfate here is also empirical. And then this mercury 2 chloride, sort of molecular. We can reduce it, so let's do that. And that's going to be just HgCl. So this is the kind of stuff that I expect you to do with just the definitions of empirical and molecular formula. Now, calculating empirical formulas. We cannot calculate a molecular formula unless we have an empirical formula. So we will calculate those first, always, unless it is given. So listen, you're just going to get moles. And remember that a Subscript tells us the number of atoms that are in the compound, but it also tells us the number of moles. So if we have a formula CH4, we can say this is 1 atom of carbon and 4 atoms of hydrogen. Or we can say that it is 1 mole of carbon atom and 4 moles of hydrogen atom within 1 mole of the compound. So those subscripts really are mole ratios. So what we're going to do is get moles. And then we're going to get the smallest whole number ratio. And we do that by dividing all of the moles by whichever mole is the smallest amount of moles. And typically these numbers are roundable, so those become subscripts. The only time we're not going to round down or up to get a whole number is if, when you calculate moles and then divide, you get a 0.5, because we really can't round that down to the smaller number or round it up to the higher number. So to get rid of that half, we'll multiply everything by 2. And then we'll get some roundable numbers, and again, those numbers become the subscripts of the compound. So if we want to know the empirical formula for a compound, here we're given some percentage composition data. It doesn't have to be in percents. You could be given just grams. You know, this is grams of this in the compound. And then, of course, we would use our molar mass to get moles. When we have a percentage, we're going to assume we have a 100-gram sample of the compound. So we're just going to change that to grams. 94.1 grams of oxygen. We're going to get moles. And you have previously learned that to get moles from grams, we're going to use the conversion factor of molar mass. And the molar mass of oxygen is 16 grams per mole. And then we will do the same thing with the other elements that are in the compound. In this compound, it's just hydrogen. So 5.9 grams of hydrogen. We know that the relative mass, or the molar mass of hydrogen, is 1.01 grams per mole. And now let me grab a calculator and do some calculating. We have 5.88 moles of oxygen and 5.841 moles of hydrogen. Actually 5.9, 2 significant digits. Let's get rid of that. Now these are not the subscripts. We will divide both of these by the smallest. So in doing that, 5.8 is smaller than 5.88. So we'll divide by 5.8 and get 1. Divide by 5.8. And it's going to be approximately 1. The calculator spits out 1.0137, blah, blah, blah. However, this number is roundable. In the tenths place, there's a 0, so we can round this to 1. Round it down. So these become the subscripts of the elements in the empirical formula. So you can see here we have 1 oxygen and we have 1 hydrogen. Now typically we write the most metallic element first. And of hydrogen and oxygen, that one's kind of tricky because remember that hydrogen can be placed above fluorine on the periodic table as well. So even though it's on the left-hand side of the periodic table, it's really a metal. I'll leave it like this to follow the rules, but typically we would write HO. All right, so here we have another example. We have 3.21 grams of fluorine, and it says the rest of the 0.858 grams of the compound is copper. So we need to subtract to figure out how much copper there actually is. 0.858 minus 0.321 is going to give us 0.537 grams of copper. And we're going to get moles. So the molar mass of fluorine is 19 grams per mole. So we'll just set up our conversion factors. 0.321 grams of fluorine. Get moles, so it's 19.00 grams of fluorine per mole of fluorine. I do like you to get into the habit of putting a number, a unit, and a substance. So this would be number 19, unit, gram, substance, fluorine, because in next unit we'll be talking about different substances and what the relations are between different substances. So 0.321 divided by 19 gives us 0.016, 3 significant digits, 0.0169 moles. Let's do the same thing for the copper. Using your tool for your mind, the molar mass of copper is 63.55, so 0.537 grams of copper. We know that 1 mole of copper weighs 63.55 grams. And that's going to give us 0.00845 moles of copper. We're not done, because once we have moles, we need to get the smallest whole number ratio by dividing each by the smallest number of moles. So I'm going to divide the copper by itself, 0.00845. I'm going to divide the fluorine by 0.00845 because that's the smallest number of moles. So the subscript that we get for the copper is 1. You can probably see just from the mathematics we're going to get a factor of 2 here. But let's go ahead and plug it in. And this is exactly 2. We don't even have to round. That's very nice, clean data. That's not a normal thing. So these become the subscripts. The subscript of the copper is 1. The subscript of the fluorine is 2. Copper being the most metallic element, we'll write that first. And remember, we don't write subscripts of 1. So the empirical formula here is CuF2. And to name that, we would say copper 2 fluoride. Now, to get the molecular formula, as I said before, to get the molecular formula, we need the empirical formula. So if you don't have that, you're going to need to calculate that first. And then you can calculate the molecular formula by figuring out what this multiplier is. Excuse me. We're going to multiply the empirical formula by this value n. And we can calculate n by taking the mass of the compound. Typically, they'll say the true molar mass of the compound is this. And we'll divide that by the mass of the empirical formula. And then, of course, we're going to round the number that we get here to a whole number. And then we'll multiply it to our empirical formula. So we have the molar mass of the compound from example 1. Now, if you remember that the empirical formula from example 1 was OH, and it says that the molar mass is 34 grams per mole. So if we're going to calculate our multiplier, we're going to do the molar mass of the compound, 34 grams per mole, and we're going to divide that by the molar mass of our empirical formula, 16 for the oxygen plus 1.01 for the hydrogen. Is going to give us 17.01 grams per mole. So you can see there, just mathematically, 17 times 2 is 34. We're getting 1.998. This is roundable, and we're going to round that to 2, and that becomes our multiplier. So if our empirical formula is OH, we're going to multiply that by 2, and we're going to get O2H2. This is hydrogen peroxide, and I know that we typically write it H2O2, so I'm just going to change that up. So once you have the empirical formula, getting the molecular formula is not all that difficult. You are always going to be given this top number here in a problem that is a written problem. If you were in a more advanced laboratory, you would come up with that number yourself. So this example says we have 0.4 grams of a white powder. It's 0.141 grams of potassium, 0.115 grams of sulfur, and the rest is oxygen. So before we begin, let's go ahead and calculate the amount of oxygen. We have a total sample of 0.4 grams minus 0.141 minus 0.115. So that means that we have 0.144 grams of oxygen in the compound. The molar mass of the compound is 859 grams per mole. That's a Haas. What is the molecular formula of the compound? So right now, we don't have enough information to solve this problem. In order to determine the molecular formula, we first need to get the empirical formula. So remember that the steps for finding empirical formula are to get moles for each of your substances in the compound. Once you have moles, divide all of the moles by the smallest number of moles and round those numbers to become subscripts. So we have 0.141 grams of potassium, 0.115 grams of sulfur, and we calculated earlier 0.141 grams of oxygen. We'll get moles. We know that to go from grams to moles or moles to grams, we use molar mass. So 1 mole of potassium has a molecular weight of 39.10 grams. I should say atomic weight there. Sulfur is 32.06 grams per mole. Oops, forgot the 6. And then oxygen is 16 grams per mole. So dividing here to get moles, we have 0.0036, 3 significant digits, 1 moles of potassium. For our moles of sulfur, 0.00359 moles. So that's about a 1-to-1 ratio between potassium and sulfur. And then 0.141, 16, 0.00881 moles of oxygen. We are not done. We need to get the smallest whole number ratio, and we do that by dividing all of the moles by whichever mole is smallest. So that's going to be our moles of sulfur. So 0.00359, that's going to give us 1. So here we're going to get a roundable 1 for the potassium. We already have the 1 for the sulfur, 0.00881 divided by 0.00359. Now we're getting 2.45, which is really 2.5. This is not roundable. So what we're going to do is double all of our number of moles. So this 1 becomes a 2, and that's the subscript. This 1 becomes a 2, and that's the subscript. 2.5 times 2 becomes 5, and that becomes the subscript of the compound. So we finally have our empirical formula that's going to help us get the molecular formula that the problem has asked us for. And our empirical formula is K2S2O5. Oops. Now we can get to the molecular formula. So to get the molecular formula, we're going to calculate our multiplier N. And we're going to take the molar mass of the compound that was given, 859 grams per mole, and we're going to divide it by the molar mass of our empirical formula here. So we know that potassium's 39.10 times 2, plus sulfur at 32.06 times 2, plus oxygen at 16 times 5. The molar mass of this compound is 222.32 grams per mole. So we'll divide here. And we'll look to see what our multiplier is. I'm getting 3.86. We're going to call that roundable. And we're going to round that up to 4. So to get the molecular formula, we would have K2. We're going to multiply that 2 by 4 to get 8. S2, we're going to multiply that 2 by 4 to get 8. And then O, 5 times 4 is 20. Here's the answer to our problem for the molecular formula. So what you should do is to take those practice problems, I think they're on a half sheet in your papers, and you are going to do those as practice and then come in with your questions tomorrow. Okay, thank you.